In this segment, we're going to look at some examples where we actually have to find K. This first example, however, they give us K. Okay, so K is the growth constant. So K is the 40%. So if we read this problem, we start with an initial amount. So initial amounts are our Q naught, right? And then we notice that T is measured in hours. So again, it's very important that we pay attention to the units on T. Okay, so starting with the formula then, A says find a function that models the number of bacteria after T hours. So Q of T, the quantity after time T, right, is found by the initial amount, Q naught, so that's the 500, times E to the K, which they gave us K, we change it to a decimal, 0.4, to the KT. Okay, meaning that letter B should be very easy. And letter B, we want the count after 10 hours. Put a 10 here. Again, when you enter on your calculator, make sure you put this in parentheses, right? So when you raise E to something, you better have the 0.4 times 10, which again, I hope you're not using your calculator. 0.4 times 10 is 4. Okay, so I am going to leave B and C for you to do for classwork. So those are your 3 classwork problems for March 25th to prove your participation. Letter C, you're asked how many hours will it take for the bacteria count to reach 80,000. That means the quantity after a certain amount of time has to be 80,000. I'm going to put 80K because that's easier. 80K equals this. You show me that you can solve that. So what becomes a little bit more challenging is if they don't give us the growth constant and we have to find it. All right, so that's what's going to happen here in number 13. So we've got our formula, Q of T equals Q naught, right, our initial amount, times E to the KT. And we're going to be looking for K. So it tells me what's happened in the first 20 minutes, that I have doubled in the first 20 minutes. So I start with 100. After 20 minutes, I'm at 200. So let's write ourselves a let statement where I am making an important note that T is the time in minutes. All right, let T equal time. Why am I not using a text box? I'll get smarter about doing this. In minutes. Okay, very important to note the units of time. And then here, in order to solve for K, remember, before I can take the natural log, I have to isolate this expression. It is no coincidence that I get a 2 over here. What this is saying is that whatever quantity I started with, right, I might say this is Q naught, and then I've doubled. So this is twice Q naught. Right? Anytime something doubles, I could just jump right to this fact that I'm going to have 2 on the left-hand side. All right, because these would divide out of both sides, and anytime something doubles, I get 2 equals E to the K. I'm looking for K, and T is 20. Okay, so I'm going to take the natural log of both sides. I'm going to start jumping ahead a little bit more. Natural log of both sides, natural log of 2, right? That would give me, I'll show it here, natural log of this, natural log of this. That's going to leave me with K times 20. So K is equal to the natural log of 2 over 20. And it's better to take k out to a whole bunch of decimal places. Don't round it off to like the tenth. I'm going to suggest that you go out at least about 4 or 5 decimal places. So, looking for this on my paper. Well, let me do it. Let me do this on my calculator. So natural log 2 divided by 20. Okay, so I got, and it's positive because I have growth, 0.0346. So take it right out 5 or 6 decimal places. My calculator will store my answer. So then when I go to do another exercise, then I just grab that amount for K, right? So that I take the whole entire decimal that goes right across the screen. All right, now in letter B, then, for letter B, we're told to write the equation that models this. So if time 0 is this moment where I start with 100 cells, so this is my Q sub 0. Like this is the point where I hit the stopwatch, right? The stopwatch starts ticking when there's 100 cells. All right, so that's how I know that my initial time, at time 0, there were 100 cells. And then from that point forward, e to the k, I'm just going to write k, knowing that k is this guy, kt. Okay, but there's my formula. Okay, so then when I go to use that formula, I'm asked in letter C, how long does it take for the initial culture to grow to 10,000 cells? So let me erase some of this. I can do letter C right here. So I'm going to grow to 10,000 cells. So you take a minute and set this up. Pause the video, set this up, and see if you can get a solution. Okay, so here's the final answer. Notice, oh no, oh gosh. Notice in the work that I did, I started kind of jumping ahead some steps. I hope you get to the point where you can do that too, because right here, I knew that I needed to divide both sides by 100. Okay, so I get 10. All right, so over on this side, I now have 10, right? And this is gone, right? Because I divided both sides by 100. Then I take the natural log on both sides, right? So natural log. So this becomes natural log. Well, I know that's just going to leave me with kt, right? So I had natural log of 10. I know I have to divide it by k. I get t. So hopefully you're okay with the way that I was skipping steps here. And then my final answer is 66.43 minutes. Okay, so let's move on to the last problem in our segment. If you study sociology, history, right, they talk about the decay of the American family. So less and less households are married, married couples as compared to how it was like back when I was first born. So anyway, if we think about something declining exponentially, remember we looked at that earlier, an example like that where it looks like this. It might decline very quickly and then level off. Some people think if they hear the word exponential, right, that should mean, right, when you hear exponential decline, you might think of it doing that. That's not the case though. Right? This is showing, when we decline exponentially, we decline very quickly at the beginning and then level off. Okay, you probably think of it happening like this, which is not the case. Okay, so let's get started. So in this case, now notice units are so important. I've said that about 10 times so far. T is measured in decades, which means when I talk about 1980, T is 1. That's been 1 decade. So I start my stopwatch in 1970. Okay, so that's T equals 0, 1970. And 1980 will be T equals 2. 1990 will be T equals 3. I'm sorry, 1990 is T equals 2. 2000, T equals 3. I'm getting ahead of myself. T equals 3. Okay, so we're going to compare this exponential decline to what it would mean if it were a linear decline, right? If it were declining linearly, then the decline would look like that. Okay, and it wouldn't, I shouldn't draw it all the way down to 0. Our married households will never go all the way down to 0. But if it were declining in a linear fashion, right, I'd go down like that. Okay, but I need to have this leveling off, right? It's not like I'm going to keep declining by the same amount until I did get to 0, right? We're never going to have 0 married households. So that's where we see this horizontal asymptote line, that at some point we're going to get to a leveling off in our society, right? And that's called a horizontal asymptote line. So anyway, let's take a look at this. Looks like I need to find K, right? I wasn't given K. So to do that, I say, okay, stopwatch started in 1970, right? So that's my Q sub 0, this 86.9. Okay. Then after 1 decade, so when T is 1, and I'm looking for K, when T is 1, after 1 decade, I have fallen to 86.66. Okay, so again, we're starting to see the same math over and over. Divide both sides by the 86.9. Right, so 86.9, divide that on both sides. 86.9. Oh, wow, these curvy numbers are the hardest to write. All right, so I'll get this, right? Then I'm going to take the natural log of both sides. Right, so take the natural log of this guy, and then that'll just equal 1K. So that's my K. Okay, so my value of K, and again, take it out to lots of decimal places. K is going to be, although actually this one I'm seeing rounds off pretty nicely at just negative. Negative tells me I'm declining, right? If K is negative, I have decline. So it's negative 0.05. Okay, so my function is Q of T, where T is decades since 1970. All right, it's right up here in italicized, decades since 1970. That equals, now I started my stopwatch in 1970, so that's how I know that I put this as my initial amount, because that's where the clock started. E to the negative 0.05 T. Okay, so find the percentage of married households in 1990 and in 2000. So 2000, T is 3. So this is just some computation. Please pause the video, get out your calculator. Remember to, when you plug in for time, make sure when you enter it in your calculator, you've got parentheses around the negative 0.05 times the 2 and times the 3. Pause the video for a minute and try C and D. Oops. Why am I not using text box? I don't know. I'll get smarter with when I should do that as I get more used to doing these videos. So anyway, these are the answers that you should have gotten. Again, this is just computational. I'm going to assume most people are okay plugging in with your calculator. That's why I hate not being in your class, because right now I'd send Emma out to check with people who aren't getting the right answers from their calculator. But again, when we look at this decrease, right, percentage-wise, we can see that it's following this type of pattern, right, that I'm decreasing, but at a decreasing rate. Okay, so I'm decreasing at a decreasing rate, which people think of the opposite, because exponential growth is increasing at an increasing rate. But exponential decline is decreasing at a decreasing rate. Remember how I showed that the other day when I drew that rectangle, right? And we were talking about half-lives, and, you know, so there's half left, so there's this much left. Half of that left, so there's this much left. Half of that left, so there's this much left. But notice the amount that I lose every time I do this is less and less and less, right? So that's where I can see this decrease at a decreasing rate, and that's what happens when we have exponential decline. All right, so we've really already talked about E. If the decline was linear, what would you expect? You'd expect something like this. We know the decline can't be linear. It could be linear for a while, right? I could have linear decline for a few years where I go down by the same amount each year, but at some point, maybe a piecewise function would be better. Then if I had linear decline, maybe for a few years I decline by the same amount, but at some point I've got to be leveling off. Okay, so I couldn't continue with this linear decline because, like I said, otherwise I'd get to a point where there's 0 married families in America, and that's just not realistic.